Hi, welcome to the Hyperplane podcast, episode 4. I'm excited to be on this podcast with my friend Bhargava Subramanian. My name is Rajesh Sampath Kumar. Episode 4 is going to be all about an exciting area of AI right now, and that is AI agents. We're going to start from the foundational capabilities that lead to AI agents, and then we're going to talk about how those capabilities evolved, what kinds of things are involved in making large language models work, in making them reason. And then we want to go from there to the field of agents. And we want to talk about, maybe towards the end, some exciting developments in the world of agents, such as agent swarms and the Claw ecosystem, which is very exciting stuff for us as AI practitioners and AI leaders. So to kick things off, Bhargava, welcome to this podcast. And let's get started. Let's talk about AI agents. Why don't we talk about large language models first?
Thanks, Rajesh. The fundamental building block of the current AI economy is the LLM, right? The large language model. If we trace back to the early versions of LLMs, the thing that LLMs do is that it's a next token prediction model. Now, let's take a few minutes to understand what that even means. Your input is a bunch of text. That text gets broken down into tokens. The fundamental building block of the input is a token. Now, what is a token? It is a word or a subword, depending on the complexity of it. A good heuristic is that it's about 0.4 to 0.6 times the word. So that's your input. This token is then passed into the LLM, and out comes a token. And this token is again passed into the LLM. This is an autoregressive model. Basically, the output feeds in as the input for the next run of the model, and it keeps going until legible output is obtained, and we can set up what the end criteria are, right? So that's what happens. So Rajesh, can you explain what happens under the hood to make this work?
If you really think about it, LLMs under the hood use something called the attention mechanism. And the attention mechanism dates back to 2017. Ashish Vaswani and several other researchers at Google, they originally came up with this paradigm where you can have recurrent neural networks that do sequential prediction of what you call tokens. So you feed a sequence of text and then you get a sequence out. But there's ways of doing that efficiently using encoder and decoder models. And when you combine these together in a very specific way, you get what's called the attention block. And this is the starting point for the attention mechanism. If I have a sentence that goes something like, the cat sat on the mat, and I mask one of the words and I feed that to the language model saying the cat sat on the, my expectation is that if my data is good, that if the model has been trained well, that it would predict mat at the end of it. And this is what attention models are doing. This is what transformers are doing. I think over the years, that core attention mechanism has been re-engineered and reimagined and redeveloped in many interesting ways. And that's what, fast forward to 2026. The reason we see all these extremely powerful models and the reason we have agentic AI, it seems to be that all of these transformer models have undergone a sea change in the years between 2017 and today. So let me go back to you, Bhargava. Where does reinforcement learning fit into all this?
The way to train models at this scale is that you need to have internet scale data, and it gets optimized for the specific tasks through reinforcement learning. So we talked about the transformer architecture, the LLMs. These are generative models. Before that, the dominant architecture was discriminative models. So the common things when I started building was like, is this transaction a fraudulent transaction or not? Will this customer buy or not? In various cases, you have a finite set of classes and you want to make predictions based on that. That's classification task, but you can also extend it to regression task. For example, you might want to say, is it okay to give loan to this person or not? if I am going to give loan to this person, what should be the loan amount that I should be giving? What should be the interest rate that I should be setting for this particular person? So this is an example of a discriminative model. Now we are in the generative model paradigm. In the generative model paradigm, if you want to generate a bunch of text, it needs to make sense, right? You need to have some way to encode that and have a way to validate. And that's where reinforcement learning comes in. The few important concepts in reinforcement learning. Do you want to explain what those things are?
Yeah, absolutely. Reinforcement learning is one of the more interesting areas of machine learning that is tied to control theory. And if you look at the history of machine learning in the context of control theory, let's say that you have a system that's like a vehicle or a car, and you're driving that car and you're taking it on an open road, or it could be off road, it could be any of those scenarios. There is a certain policy through which you govern the movement of the car, and the policy could be defined in terms of your steering input, your accelerator input, your brake input, and so on. Now, if you were to think about how a machine learning system could learn how to drive a car, it would actually try to predict the next state that is going to be required for the car to move in the desired direction. So the desired direction is going to come from your landscape. And when you say desired direction, that comes with this concept of reward and penalty. So a reward is something that is a positive reinforcement for the system that's learning to predict its optimal policy, and the penalty is a deterrent for using a certain policy. So if you iterate on the set of states, you're going to eventually learn the best optimal policy for driving a car, right? Now let's take that idea and apply it to the concept of machine learning, where you're trying to build something like ChatGPT, right? So we all know ChatGPT probably came out in late 2022, and it kind of took our breath away with how it was able to create coherent passages. Of course, things have come a long way since then, and things are much better now than they used to be in 2022, despite all the misgivings that we have about these models. But one of the key steps in the process of building ChatGPT was actually reinforcement learning. In fact, that probably brings me to the recipe for how we should train a GPT. And GPT really stands for Generative Pre-trained Transformer. So I want to go over to Bhargava. How does reinforcement learning fit into the scheme of GPT?
Well, let's try to understand the various components that go into building a large language model. So it has broadly 5 dominant steps, and we'll talk about it. The first is called pre-training, where there's an enormous corpus of internet scale data, and it just uses what is called self-supervised learning. You just give the data and then ask it to learn something by itself. That's the step one. Interestingly, this is where the most amount of money is also spent when you're building a large language model. When someone tells that it takes them $10 million, $50 million to build a model, about 70% to 80% of the money is just gone in the pre-training step, and it takes many weeks. Interestingly, the earlier model took many months to even get to this particular pre-trained state. The second step is called mid-training. Early models didn't have mid-training, but now the current accepted paradigm, there is mid-training. Your mid-training is where you go from internet scale data to a slightly tractable, curated data, so that you can focus on specific kind of tasks that it can work on.
So Bhargava, we were talking just before this conversation about textbooks are all you need. Isn't it exciting that you can spend millions of dollars training in an unsupervised fashion, and then with very specific data, like in the textbooks are all you need paper, which led to the Microsoft Phi series of models, right? PHI. So it led to that series of models. It's remarkable that with a very specific set of data, you can get incredible performance just by that kind of mid-training step.
Absolutely. And this is also something that gave rise to what is called small language models, that you can now take a large model and then distill to a smaller model, or just do mid-training and then do a smaller model that works only on specific domains. Which brings us to the third part of the process, which is called supervised fine-tuning, also called instruction fine-tuning. Here, what is happening is that you're giving a question-answer pair. Like you create a bunch of question answer pair, and then you ask your model to predict. So it is a question, and you give that question as the input, and then you want to see if the answer came. The algorithm to make this work is reinforcement learning. Your created answer, your ground truth, and the answer it created is not the same. So somebody has to make a decision if they are right or not. And that is what gave rise to the first implementation of reinforcement learning in large language models, called reinforcement learning with human feedback. Rajesh, can you explain how that works?
Yeah. RLHF, going back to what I said earlier, is all about learning the appropriate policy. When I am using a large data set, like an internet scale data set, to tune and train my model through unsupervised learning and then supervised fine tuning and so on, what actually happens is that the outputs that are generated by the model may still not be in tune with what users expect. And reinforcement learning with human feedback is where the reward on the one hand and the penalty on the other hand are provided by a human interacting with the system. And as the machine learning model is able to pick up penalties and rewards, it's able to be steered in the right direction in terms of the outputs that it generates. So I think RLHF also led to another innovation from DeepSeek, Bhargava. So do you want to talk about that?
Yeah. So as you rightly pointed out, here validating introduced a bottleneck. Humans need to give subjective feedback.
Is it scalable? Do you think RLHF is scalable?
I mean, if you employ a lot of people, then
Yeah.
yes, you can do it. But it introduced bias, right? Like you want to get to a place where this process is automated and you want to be a bit more certain and predictable in your training process and output. And that that was like the big thing that DeepSeek introduced. And we are like only 12 months into that cycle. They introduced what is called RLVR, reinforcement learning with verifiable rewards, where you already know that this is the output and this is how I'm going to train, and this is the policy, the reinforcement learning policy. Can it be learned as part of the training process itself? So instead of a human manually voting yes or no, it moved into automated process, and different policies were generated, and it was able to figure out which is the one that really work, and that's part of the training process. The last step in the training process is alignment, right? So can you talk about what alignment is and where it fits in?
So there's a lot made out of this in the AI industry with all the big labs. They focus a lot on alignment. But what is alignment actually? Alignment is what allows your model to be put into different kinds of contexts in the hands of different users and not produce results that are unethical, results that are dangerous, or instructions or outputs that are potentially hazardous. There's multiple ways in which we can measure this. Historically, there have been frameworks like ragas, which have been used. There's different measures of the outputs from an LLM, such as the groundedness of the machine learning model, the toxicity of the results from it, the bias that might be inherent in the model, and so on and so forth. And these concern not just the factual accuracy of how models perform, but also the value systems that we want to have them align with. And these value systems are obviously subjective things. The value systems that you might find in California might not be the same as that you might find in the Middle East. And that might not be the same as what you might find in India or China. To make the model aligned to these different situations is an important part of building a model for production scale release and a rollout that is not just effective in one situation, but also broadly effective across multiple situations. So I would say that that's a layperson description of what alignment is. So I want to now talk about the other layers that have led to the whole process of building agents. Just generating text would not have been enough, because the real world is much more than text. There's a lot of signal out there in terms of the images that we see with our eyes and the sounds that we hear, not just images but video, right? So the dynamic nature of the world around us is really a signal for artificial intelligence. So how do we build models that follow the same paradigm of being a generative pre-trained transformer, a GPT, but somehow also incorporate some additional capabilities for these different modalities of data?
So interestingly, OpenAI came up with this models, 4V, 4O models that were inherently multimodal. And the way to train these models is to give question answer pairs. So if you're going to train on images, so you're going to explain what that image is, and then they are part of your training process. So that allows you to now go and then learn this image pair. Interestingly, models and image followed a different path to how the LLMs work, which is autoregressive next token prediction, right? They followed what is called the diffusion model. Can you explain at a very high level what diffusion models are and how image generation really works?
Yeah, that's a fantastic segue. Bhargav, as you described earlier, text generation happens in the current paradigm through next token prediction. So, what the LLM is doing is, having been trained on very large internet scale data, it is sampling from that distribution of data that it has, which is internet scale data. And the subsequent steps, such as supervised fine tuning, instruction fine tuning, reinforcement learning with human feedback, or RLVR, all of these techniques are really about how we can sample more efficiently. It's still about sampling. The fundamental problem is still about sampling. With image generation and the related class of models that do audio generation and other generative models that generate things other than text, right? It really started from autoencoders and denoising autoencoders, which were a class of encoder models where you learn a lower dimensional representation of high dimensional data. Like, if you take any image or any video, it comprises of multiple pixels and pixels that vary over time. And all that is by definition higher dimensional data, because you have the R value, the G value, and the B value, and you have the time component of it. So, with all of this multi-dimensional data, this higher dimensional data, you want to find a lower dimensional representation of that so that you can effectively compress or represent the image. Now, starting from that innovation, we started going towards denoising autoencoders, and that eventually led to a class of models called diffusion models. So diffusion models are all about how you can take effectively a field of noise and systematically remove noise so that you can generate an image from that. And the interesting thing is, those are tied to text. So you can have text input, and as the text that is received is different, the way in which denoising happens, or the way you add noise, or the way you remove noise, is different. The mechanism is different. So this is a fascinating class of models. Interestingly enough, even in the text paradigm recently, there has been an innovation around diffusion text models, but I won't go into that now. You talked about image generation, and we've talked about how image and text data are both used in modern multimodal models. Let's talk about the whole process of reasoning. I would like to understand from you what reasoning is in the context of an LLM.
Okay, so let's first motivate why this is important. An LLM, next token prediction, you give an input, it keeps generating one token at a time, and then together they form some coherent output. That's what it is, right? But you want to now talk about getting a very specific kind of answer. So first you ask a question and then it gives you an answer, right? So an example for this could be, name the 7 wonders of the world, right? It's going to list all 7 wonders of the world. That's an example of where you're just relying on its intelligence. The input that you provide, the text that you ask, the question that you ask, is called prompt, right? The prompt, you send a prompt, and then you get an answer. This prompt is just direct question and then I get an answer. This is called zero shot prompting. I'm not giving any inputs and insights, or I'm not helping the model in any way to go in some direction, right?
Absolutely.
Now, what we can do is that as part of it, we can also start giving it certain examples, right? Rajesh, do you want to give a few short example and then explain what it is?
Let's say that I have a bunch of sentences that I want to call positive or negative, and I have customer feedback that has come in from my customers, and some customers have given me an emphatic positive feedback, while other customers have given me negative feedback. I can say that this is an example of positive feedback, and this is an example of negative feedback. And as a result, what do you think this particular new example that I'm giving you is? Is it positive or negative, or where on the spectrum does it sit?
It's a great example of doing sentiment analysis, where you're doing a sentiment analysis on customer support data by giving some examples. So the problem with both zero shot and fuse shot is that it's brittle. Like it's
You're dependent on the corpus, Bhargava, aren't you? You're dependent a lot on the corpus with respect to zero shot, which means your corpus has to be that much bigger, and the model has to be trained extensively on the corpus.
exactly, because now this is internet scale. It is not, in spite of having mid training, it's not super hyper focused on just customer support data. In this example, it's going to now not be very consistent, right? It's going to be brittle. It's going to be breaking in ways which you wouldn't have imagined. This led to the third paradigm called chain of thoughts, where in addition to giving this example pair, you're also going to explain why that is the case. So now, as part of your prompt, you're going to tell that, oh, help me, I'm going to give you a customer support data. You need to classify this as happy customer, sad customer. And then this is my example. This is the text, and this is a happy customer because XYZ. This is the customer support chat, and the customer is an unhappy customer because of ABC. But this also turned out to be brittle. This was quite common for a few months until a new class of models came, which is called reasoning models. So giving a set of examples to bias it to very specific kind of output, to now can it really reason, right? Like, how do we ensure that we build models that actually reason? That led to the entire field of reasoning models. Rajesh, can you explain what the fundamental building blocks of reasoning models are?
Yeah, reasoning models are interesting because they are still based on the same paradigm. We are still predicting tokens, right? But there's a certainly difference to the way the predictions are happening. Every time you ask an LLM to generate a token, right, it does it in a slightly different way. I mean, you can try this with any of the older chat GPT type LLMs, where if you feed in a question, it might give you just a slightly different response every time. What a reasoning model does is there's a specific step in the reasoning model training process. And we talked about the training process earlier, which includes a number of steps followed by reinforcement learning. Now, there's a training step that is called post training. And the objective of post training is to represent the inference process as a search problem. Now, why is this important? Every time, as I said, you prompt an LLM, you're going to get a slightly different answer. Imagine if you had all those predictions lined up. It would look like a sequence of tokens multiple times. You'd have an entire forest of tokens to search from. And what a reasoning model does is, through thought tokens, it goes through and it is able to figure out what the appropriate output should be. So this sort of grounds the whole process of generating output, compared to before, where you could be getting any sequence of the whole span of possibilities of tokens that we talked about, right? So there is a reinforcement learning loop that is specific to reasoning. Can you talk us through what that is? What is that reinforcement learning loop? What is actually rewarded and what is penalized as part of this?
So RLVR, right, that really transformed how reasoning models came into picture, because now, as you rightly said, reasoning model treats inference as a search problem.
Yeah.
You actually have multiple generations and then multiple kinds of answers, and you need to figure out which is the right reasoning. You have the reasoning trace as part of the training process, and whichever one actually matches gets rewarded. As you said earlier, about it gets rewarded, your policy gets updated, and that keeps going on. Outside the scope of this particular episode, but we'll do a later episode, there are policy optimizations like DPO, GRPO that are used to optimize this particular process. This is entirely part of the training process that requires no human intervention. It uses the different reasoning trace, and whichever one matches well to the ground truth, it keeps optimizing until we have a model that is optimized, where as part of the training process, the reasoning is baked in by using a thinking token, right?
By using thinking tokens. Great. So I want to talk about an allied capability for reasoning models. What if you don't have all of that knowledge that comes from having a huge internet scale corpus? Or what if your knowledge was cut off somewhere in 2023, 2024? You had to build a model and you thought, look, this model is good enough. How do we make the model really adapt to the context of any user? And if you train a model today, you want that model to be somewhat relevant a year from now, 6 months from now, without having to release new models every couple of weeks, which would be prohibitively expensive. Let's get into that, Bhargav. I would like to understand how this kind of generation process can be made more robust. What are the revolutions that we have seen there? Now, we've talked about reasoning models. What has happened in the AI space with generative models that has led to other kinds of sophisticated reasoning?
Okay, so everything that we talked about is only based on the knowledge being encapsulated within the model, right? That's not always true, as you rightly said, that the training could have been cut off. It's also that there are company specific data, like you talked about customer support data. Like customer support data is not out there in the public domain. It'll never be out there, right? That's proprietary to the company. And then you want to use that to do some reasoning and understand a bunch of things. But they're very specific to either a person or a company or a vertical or a country. At different levels, there are information that are very, very proprietary, and that's not part of your training data. To do that, the most common thing that came out is called RAG, Retrieval Augmented Generation. The way it works, Retrieval Augmented Generation, is that as part of your input to the LLM, it, along with your prompt, goes the attached document, and then your reasoning, your LLM generation first looks into your RAG to see if there's an answer in the document. If it's not, then it relays back on the underlying model. To do that, it requires this concept of embedding and then vector DB. Can you explain like what these things are and how they fit in?
Absolutely. I want to touch upon one important concept in the context of language models before we go into the details of RAG, and that is the context window. And the context window is at the core of so many things. Even now, as you look into the world of agentic AI and what is being built today, context has become an important thing. There are a lot of people talk about. And the reason is these models that we are talking about, large language models, you cannot feed infinite amounts of text as the input for every given inference. There are some limitations, and the size of that context window, it really refers to the tokens that you can feed into any given input to the LLM. This is something to keep in mind because as we are building with large language models, managing this context is important. This context comprises text instructions, which we give to the model because these models are instruction fine-tuned, as Bhargava explained earlier. It could comprise of specific user requirements that might be embedded in a prompt. And as Bhargava has been explaining, in the retrieval augmented generation paradigm, we are taking data from the client's context to the user's context and embedding that as part of our input to the model. So this context is going to be an extremely important part of retrieval augmented generation and also some of the subsequent capabilities that we will uncover with LLMs. Around 2022, there was a lot of activity in the space of retrieval augmented generation because ChatGPT 3.5 had launched, and that brought a sea change in the capabilities of these models. It was really the first big model to make it big time, and enterprises started taking generative AI seriously. And to make this problem of applying the LLM to their enterprise context work, they had to start converting their text data into something called an embedding or a vector. And we've talked a lot about large language models, but there's also another class of models called embedding models. And these embedding models, all they do is find a lower dimensional representation, a numerical representation of text. And that numerical representation of text, whether it's a lower dimensional representation or a higher dimensional representation, the objective of that is to be able to reason about similar passages or dissimilar passages of text. And by doing all this, you're giving the large language model the ability to reason about the text that is present in your system within your organization. And you give it the ability to perform different kinds of tasks, such as reasoning about an embedding using vector databases as part of your system can also help you find similar passages of text or find similar strings. So I want to go into another interesting topic. We talked about the context window now, and we talked about retrieval augmented generation. Isn't it true that there's a lot of things that the LLM knows by itself? Is there any need for us to have any additional memory? Is there like a RAM that I can put into an LLM that makes it remember something? Bhagavad, do you want to get into that?
Yes. So we now started with base knowledge that is embedded into the model. And then now we've started talking about how can we have an additional data component like vector DB to do that. On top of it is the concept of memory, which is all about user behavior. Context is what happens with externalized data. But we started talking about 7 wonders of the world. I want to know how Grand Canyon was formed. I want to understand how the Ganges flow. All of this now gives a sense that I am interested in geography, right? Now, there are two parts. One is that in my current conversation, so we call it a turn. Like my turn, I ask, I get an answer. I do multi-turn, I ask multi questions, and then there can be something that could be understood about the intent of the user. So you can take all of that to pass it to bias the answer based on what the user is doing in that session. So that's in context memory. Also, the second thing is it could also be episodic, which means that I've done like 100 sessions. Every session, it has learned something about me. For example, it knows that, oh, I'm interested in cricket, I'm interested in basketball, I'm interested in AI. So at various parts, it has learned something about me so that the AI could be influenced to answer in a specific way that makes sense to me, right?
Where you're going with this is the episodic memory, the long-term memory, the short-term memory that we are familiar with. Are they part of the broader system, or does the model itself hold that information? Isn't it more the context that is being primed in the appropriate way so that the user's preferences and the user's history is made useful in that context?
Absolutely right. Whatever the model has learned is not changing until a new version of the model comes. These are all, you're augmenting what you can use the model with. So you're enriching that information by additional information that can go through RAG, additional information that can go about the user, additional information that can go through what kind of interactions the user has, so that you can get better and better responses. So that's all managing the context window better.
There's a lot of engineering involved in AI, isn't it? Just in that context, and I'll touch on this just for a brief moment, that whether it's retrieval augmented generation or building memory, and we talked about reasoning models, post training, these are all a combination of machine learning capabilities and engineering capabilities as well.
Absolutely. They go hand in hand. It's not just algorithms, they need to make some things work. But let's expand this paradigm. Until so far, everything that we have seen is that I ask something and then it gives me an answer back, right? That is in some sense like going to a library or an encyclopedia and then reading something. The true power of AI comes when I already use a bunch of apps and other things, and then it can take some action on top of it. So the first kind of innovation that happened is called function calling or tool calling. Can you talk us through what those things are?
Absolutely. During the evolution of the OpenAI GPT series of models and also Anthropic Claude and even some of the open models a couple of years ago, 2.5 years ago, it became obvious that, as Bhargava said just now, you cannot actually operationalize a model in the real world unless there is some way for the model to act on that real world scenario. And one way to do that is by providing tools. And I think one enabling capability for this is code generation. We've seen how in the previous podcast as well, we talked about Anthropic and their path to AGI as being code generation, right? Now, code generation has been a front and center capability for Claude. In fact, that's what they pride themselves on. it also has been an important capability for a number of other open source and closed source providers. OpenAI's GPT 5.3 Codex is a fantastic model. The Codex application is amazing. We'll talk about that in the later part of this video as well. But I think code in general is an enabling capability, because instruction fine tuning and the fact that your model can understand instructions and choose the appropriate instruction based on input prompts can be a powerful ally when you're trying to use that model to build code bases, right? And I talked about tools a moment ago. An important consideration for anything that is non-standard, where generating a piece of code which then has to be run as part of a runtime and then has to execute a result, when that is not an option, and when there are already systems out there which have proven connections, which have proven interfaces, where you have a way of accessing a database, or you have a way of accessing a sensor and getting a reading, or you have a way of accessing a camera and taking a photograph. All of these are capabilities that we can give to models. And that's what tools allow you to do. Tools in the specific context of LLMs are included in the output tokens, as part of the output tokens, as what are called tool tokens, right? So you have parts of the output that include the tool component of it, and then parts of the output that include the regular text or instruction or other components of it. And all this allows an LLM to really act upon the domain by the use of these tools. Going back to the example of driving a car, if you think about how that person is driving a car, it's by using the different tools that are given to them, whether it's the steering input or the brakes and the accelerator or other kinds of tools that may be at their disposal. In much the same way, if you think of an LLM as learning how to navigate through its environment and taking certain actions upon the environment, the way that it would do that is by predicting all the tokens that include the tool tokens, which help us actually act on the domain, right? In this context, Bhargav, I want to get your thoughts on model context protocol. It's a powerful technology, isn't it? And at the same time, where do you think it stands as of 2026 in February as we are recording this?
So, I mean, all this is like less than a year old, but let's first explain what model context protocol is. Okay, tools. So these are external applications or external functions that you can call. Let's take an example and then walk through it. I open the LLM of my choice and I ask, should I be wearing a sweatshirt, a pullover, or a t-shirt? Literally, that's the question, right? Now, it first needs to go figure out the location that I'm in. So I'm in Bangalore. So it needs to first understand the weather prediction, and then it has to figure out my likings, and then has to give me a recommendation. The model already knows my preference for my dress based on my past interaction, so that's part of the memory. And then it now knows that based on the question, it needs to go check the weather. Based on the memory, it knows that I'm in Bangalore and it needs to get the weather for Bangalore. To do that, it needs to call the weather API, right? Now, for an LLM to configure every single API for every single vendor out there, it's just not possible, right? So what MCP allows us to do is that it allows LLMs to have a standard interface. The provider will have to configure it so that it can accept this request from an LLM and then pass the answer. So here, the weather MCP will be called with the city as Bangalore, and then the MCP server will respond with, oh, today's temperature 23 degrees Celsius. It's not a time where you have to wear a sweatshirt. Your t-shirt is good, and then give the response. So that's what happens. But having said this, because of the thing that you just said about code gen capabilities, in the last 12 months, the biggest leap for everyone has been in code generation. So LLMs have been able to generate better code, reason about it, and then take decisions based on that. Like if all of this are just deterministic code, it just doesn't make sense to do MCP. So the code generation happens. Rajesh, can you explain to our audience in the specific instance of tool calling, function calling, MCP, how this code generation happens, and maybe also touch upon why people really frown upon NCP and then where things are going?
That's a good segue actually into certain other capabilities. And we were talking about tools in general and instruction following. Just like text generation requires us to train models on large corpuses of text from the internet. As Bhargava mentioned earlier, we can have large code bases that are part of that corpus. And we know that in open source projects on GitHub and elsewhere, there are large repositories of code. In a nutshell, all these are different kinds of programming languages, each with their own syntaxes, each with their own modalities of writing code. Just like we have linguistic complexity in the form of English being one kind of language and say Hindi or French or Japanese being another kind of language, you have different computer languages which also form their own uh, complexities there. In a nutshell, the process for training a next token prediction engine, similar to what LLMs do for language, is not that different for code. It's the same process would be followed, but the big difference here is going to be that the code that is created at the end of it is something that can be formally verified within the computer by execution. And, Bhargava, in the last podcast, we talked about formal verification and why that's such a great capability for generative AI, and why that in fact might be a big deal in terms of how effective these systems are. Now, let's go to MCP for a second. MCP is a capability which has evolved in the last, I would say, year and a half. I was listening to a very interesting discussion on the LangChain forum with Andrew Ng earlier today. And this discussion was, in fact, from 8 months ago. It's not even a year old. And the interesting thing that I found about that discussion is that MCP was being talked about as an extremely important new paradigm. To be fair, even though that discussion is 8 months old and it's outdated today, and a lot of people think that MCP is not the correct abstraction, there are still many pockets of the industry where MCP could be used. One area that I thought of, just as you were making the point about whether and what you should wear for your personal assistant, imagine the connected home, which is a great example of TV having a different protocol, from lamps having a different protocol to an air conditioner or a fridge having a different protocol. If you were to ask the question, what are the seasonal vegetables that I should buy next week, to your assistant, and it's connected to your fridge, it's connected to the ambient temperature controller, it's connected to maybe other aspects that make your smart home work. In the future, we might even see a capability like this unfold, where you can ask a question like this and get an intelligent answer in terms of what should be stocked in your fridge. So that's an example of a situation where MCP could be a useful protocol, where every provider might have their own abstractions, their own stack on top of which they expose an endpoint or they expose a capability. But for your LLM or your agent to work with all of those different systems, it's essential to have that intermediary protocol, which is what MCP does so well. So I want to spend a minute on context, going back to context, because we've talked about tool calls, we've talked about tool calls, we've talked about MCP, we've talked about code generation as a capability. Isn't all this a lot of stuff to put in the context window? Are the context windows really that big? Are they capable of handling all of this?
In some sense, the context window has been increasing, right? Like from 4,000 to now we have million context window. It keeps increasing, but is the increase in context really leading to superior output is still debatable. There's this entire concept of context rot. As you start filling up the context to the brim of its context window, the model starts to degrade. And then a lot of people have just tried various forms of prompt engineering. What people are doing is that they're repeating the important point multiple times so that they can bias the model to act upon it. Yes, context engineering is a thing. Everything that we have discussed so far goes into the context. The prompts, the memory, MCP, the tool calls, the function calls, any additional information that you give are all part of the context. Now, of course, there are enough studies that tells that if you fill the context window to its brim, there's a context rot happening.
What is context rot?
Context rot just means that as you start filling the context, the ability for the LLM to respond in a useful way reduces. So So think of this like a curve that has diminishing returns, right? The models, obviously, the underlying models are getting better at it, but we still have an issue where if you're going to fill it to the brim, it becomes a challenge. So that's why the context engineering is an active field where people figure out how do I give the most optimal input so that I maximize the kind of output I get from my model. An interesting thing to point out here is that the input that I send costs money and the output costs money. So even if the context size is increasing, the number of tokens that you send in is not free, it's going to cost money. And the number of output tokens that you're receiving also cost money. You have to balance this. Okay, now that we talked about context engineering, let's move on to the most exciting thing in the AI space right now, agents. Rajesh, can you talk me through a very simple definition of what agents are and why are we all excited about it?
All right. Agents are basically long horizon planning and tool use systems, right? When you look at the history of agents, you can go back to the mid 2000s, probably the mid 2010s as well. There have been different manifestations of what agents refer to. In the mid 2000s, people studying swarm intelligence and areas of physics were referring to agents as independent actors that collaborated and that were able to produce a net effect on their environment. And Melanie Mitchell, who's an AI pioneer and who's worked in this space, has written a great book that actually discusses this. In the mid 2000s, we saw OpenAI in their initial experiments come up with the OpenAI Gym, and back then reinforcement learning was the primary mode of thinking around agentic AI. People thought that reinforcement learning would take us to the target of building a system that can reason about the environment, act based on some kind of policy that we talked about earlier, right? Now, fast forward to 2026, and we have, as we've discussed earlier in the podcast, a number of capabilities that have enabled software systems to speak to and benefit from large language models and all their capabilities. So, what does that provide us? Agents are like complicated if else logic that have an LLM at the center. I think we were talking about this earlier, and you made this statement. Is it just simply a bunch of if else statements or a for loop that is running an LLM? And I think that statement might be said in a lighthearted fashion, but it's probably true that a lot of agents are simply repeated calls to an LLM. And with the changing context of what is happening in the environment, how the environment has responded to the agent's action, the next task in the sequence of tasks to be executed is planned and executed by the agent. So the important thing is that this happens over a long horizon. An agent is not an entity that only works in a short horizon, like an ephemeral one or two inferences or a few inferences, but it's meant to work in a repeated fashion on specific types of tasks or for specific things on a long horizon. These agents are given the ability to use memory. They are given the ability to learn about the context of the environment around them. They are, of course, given the ability to send their data to an LLM and receive inference back from an LLM. And this is the way in which these software systems are being engineered right now. Bhargava, you've seen the agentic AI space as much as I have. What are the different agent paradigms out there? What have you seen out there?
So you just started with one agent having a tool, and then it repeatedly uses either the knowledge from the LLM or calls the tool as needed, and then runs it until it accomplishes a particular goal. That's the simplest way to using it. The next one is an agent with multiple tools that can now, based on the output that comes from the LLM, can decide to invoke one of the tools and then takes action, and that goes on. That's the second thing. But the extension of this is that there are multiple agents. They are in serial, right? So the simplest way to think about this in an enterprise context where we both have worked, it's a workflow, right? Okay, somebody has traveled and then they come back, and then we've all done this.
Yeah,
it's super painful. We have to submit claims, and then the process has to happen and come, right? So that's a workflow. When you travel, you have to collect your bills, you come back, You have to digitize it, you have to go to a form, and then you have to submit, and then it needs to go through an approval process, and then the payment happens. And this can take anywhere from 2 days, which is mythical, and it takes about a month or so for the processing to happen, which is kind of more typical. 2 to 4 weeks is what most processing times are. So this is a classic example of where it's in a workflow and then AI agents can act. It's a classic example of a workflow in place.
And the reason we would use an agent for this kind of a linear workflow where things are well known is because there could be noisy data in an invoice, right? So two invoices may not look the same. They may have huge variability between them in terms of where different data points are and where the total is, for example, or where the name of the business is. That's to give you a very simple example. But there could be other reasons why people might want to use an agentic workflow. People ask the critical question of whether to use an agent for a certain business process or for a certain workflow automation task. And that is a valid question. In my view, wherever you see that each individual step involves some non-negotiable variability that can only be solved by using an agent that performs some long horizon task, that's exactly when this kind of a workflow really works out, isn't it?
So when you want to drive efficiency, this is something that naturally falls in place, right?
Yeah.
So ambiguity is something that agents in a workflow system will not resolve, right? So that's something that you only know that there's some intelligence encoded in here and you have access to the tools. An example is that corporate policy. Like there are some corporates which does not reimburse, say, alcohol bills in dinner. So somebody uploads the bill and you'll have to check that, oh, is the dinner bill cannot exceed $300. So you'll have to go and then check. So when these kind of questions happen, there's already a document. So it takes the document. We talked about it earlier in the podcast about embedding. It does this match, and then based on it, it is able to take decisions and act upon it, and then either accept the bill or reject the bill. There's another class of models which is what agentic AI is, which acts in the ambiguous decision-making paradigm. Can you talk about it?
Absolutely. You talked about as linear flow where you have certain well-defined steps or at least broadly well-defined steps, and then you need specific long-running tasks to be solved by agents, and those agents hand off the work product to the next agent and so on. But then there are other problem statements where the agents might have to sort of work with each other in the process of solving a problem, even a specific problem. And the interesting thing here is that the communication is not always preset and fixed and decided. It could vary based on the situation, right? There could be, for example, an invoicing process or a manifest checking process in a bank. Maybe there's a shipping manifest from somewhere that they want to check to determine if everything looks okay. And each of these is multiple pages. In some cases, you can have 300, 400 page manifests. And if you need to check all those manifests, then you need to divide that work amongst different specialized agents that are each doing their specific thing. And the important thing is that between the second page and the 20th page and the 30th page and the 300th page, there may be a lot of context that's preserved within the document that a human who's able to look at that document is able to understand. But for an agent that's looking at a specific page, that may not be able to do that. So when you look at this scenario, you need agents to be able to speak to each other. So there's protocols like A2A, which is a Google protocol. There's also multiple other protocols that are focused on agents and how they can communicate with each other. Of course, there are standard protocols like the message queue protocol that we use for any kind of asynchronous message based system. There are a lot of developers and people who are techies who are listening to this might identify or recognize. But there is also a way to build workflows that use these agent to agent protocols because they consider a number of things that are specific to agents and that are not necessarily generic to any application software or backend, right? So I think the distinction here is that as we become more and more sophisticated with the use of agentic AI, agent to agent communication becomes a first class consideration for any agentic system. And I think, especially when you have multiple agents with very well defined identities or very well defined workflows that are very well defined logic, that is part of them, agent to agent communication becomes very important because the handoffs between the agents, the way they come together and execute, those things require agent to agent communication, right? So we are firmly in the realm of multiple agents now because we're talking about agent to agent communication. What is the future of something like a fleet of agents or agent swarms? We know that they are relevant for some problem statements, but do you foresee that as being a very important thing? To give you context, within Cloud Code, which is an extremely effective coding agent, there's just one agent, and that itself is doing so much work for me. So where do I need a swarm of agents? What are the potential benefits? What are the pitfalls that you can imagine with respect to these?
Okay, so this comes to some of the most exciting things happening in the space. But before we come into the fleet of agents and how we can manage it. So, for example, as you rightly pointed out, a workflow is just a linear path for this agent and agent A, agent B, agent C. And the fleet of agents, the way it would happen is there's agent A, agent to agent protocol. So now, so agent A can decide, oh, to accomplish this, I need to talk to agent A. And then once the output comes back to agent A, based on this, I need to talk to agent D. And then I pass it on to agent B. So it can keep going on in a very non-linear probabilistic way where the agents coordinate amongst themselves to accomplish the task. And we are seeing, as you rightly pointed out, there are like non-trivial number of cases where that's how human decision making happens.
Yeah.
And agents have finally started mimicking how, as humans, we coordinate and then solve a problem. Agents are coordinating amongst themselves and start solving the problem. But to do this, let's take the specific example of Claude Code, where it's just there's an agent and then it's able to accomplish a task, which is that you've given the goal, create a landing page for me, and then it comes back with a killer landing page. It needs to first have the text, a design system, it needs to know what components need to be there. It's a whole bunch of things that needs to happen, and that's all something that it is able to resolve. It happens within a very confined environment, and the agent interacts with the environment to make this happen. And that's called harness, right? Can you talk a bit more about what harness and what harness engineering is? And then we can go and then talk about the exciting aspect of how a fleet of agents can work.
Yeah, that's an exciting question, Bhargava. I think harness engineering is something that I read about recently, and the formal terminology seems to have come through Greg Brockman's post. He's the OpenAI CTO, if I'm not wrong. Harness engineering is really a set of, you can call it a set of constraints. It's a set of tools. It's documentation. It's anything that enables the core model to deliver value. And that value could be different in different contexts. In the case of Cloud Code that we are discussing right now, it would be the actual code or tests or the outputs that are generated. But in a different context, in a different business context, where my objective might be, say, to produce a PowerPoint presentation for my audience, or to produce a business report, or maybe to turn on or off a particular sensor in a factory shop floor, or maybe I want to do a certain kind of check on a patient who's in an emergency room or a ward. For all these situations, the constraints, the tools that you need for agents to effectively perform that task, the constraints under which they have to perform that task, and documentation and the context that they require in order to be effective at that. All this is what is provided by the harness.
This is awesome. So there's a model. For example, in Cloud Code, now you have like Opus 4.6, and it's going to generate code, constraints provided through prompts, and then there's documentation. It's a list of things that you can do. It has instructions, so which means that these are the kind of tools you have access to. These are the kind of things that you can do.
One pattern that I see is that there's a lot of text out there. There's a lot of human readable text that is managing context, instructions, tools, even skills. There's this meme or a phenomenon in the circles that we are part of in generative AI, as well as on X, the parts of Twitter or X that focus on machine learning. Skills is a markdown file. I think that is the meme that is going around these days. So when you talk about skills in the context of a human and what they're able to do, we know that there's a certain set of attributes that we have, capabilities that we have developed over time, whether it is being able to sprint or run or juggle or whatever it is that constitutes a skill for a human. It could be subtle things like writing or presentation or public speaking. But for an agent which is capable of broad based natural language processing, natural language understanding, instruction following, instruction planning, code generation, because all these diverse skill sets are the potential that an LLM possesses, right? It's all really part of the model that comes out as you train it. So this harness becomes extremely important. As you can imagine, those markdown files that we're talking about that define an organization's constraints, that define the rules and the documentation, the tools that you have to use and how not to use them, that becomes the valuable context. We talked about context engineering earlier. The context that goes into the agent is all the stuff that is in the harness.
This is so fascinating, right? So I've been listening to talks around harness engineering. Sasha Rush Cursor has given an amazing talk around how Cursor is optimized for this. So now the thing is, if you see these models, we talked about how LLMs are trained, but LLMs work on a very confined space, which is what we've already discussed. To make it work for you in a real setup, the key differentiator is the harness, right? So it's two sides of the coin. They go hand in hand. You cannot have harness and the model separate. So sometimes it's the model that's optimized for the harness which is optimized for the model. They both are trained together to ensure that you accomplish a particular task, which is why you can take the same Opus model, use it in a different IDE. The kind of output that you would get is not as awesome as what you would get within Cloud Code, right?
Amazing. When you're just a consumer of these tools as a developer, or if you're listening to this as a developer and you're just a consumer of Cursor and you think, yeah, I'm just going to select Cloud Opus 4.6 from the model list and I should be fine. That might not just be the case, right? Because it's the model plus the harness that results in the kind of high quality output that we've seen. We've seen this with Codex as well. There's GPT 5.3 Codex, which is an extremely strong model. There are the benchmarks that you get with models, and then there are the experience that you get, I should say, with using a tool like Cloud Code or Cursor or any other tool. It seems like even though the potential of the model is extremely high, even though the model can produce incredibly good outputs in terms of reasoning, humanities last exam, RKGI, you name it, right? All of the benchmarks, it's really very good. Even though that's the case, sometimes the feel of the model is off. And we know this as people who have vibe coded applications, and the feel of the model might not be there because of the fact that the harness is not right. Is that a fair statement?
That's fair. So the analogy I'd love to give was that there is an athlete who has the potential to be an Olympic star, right? But that alone is not enough. So you might have it in your genes, you're really talented, but being talented is not the same as being skilled. Being skilled is that you're in the right place, are you disciplined, you have the right coach, the right nutrition, the right training regimen,
Yeah.
are you on top of your fitness, are you on top of your mental capabilities? It's the same thing with an LLM that at this point in time in February 2026, the key differentiator is your harness. And we have seen that work well in the coding environment with Cloud Code being really good in its harness engineering. I was surprised to know that the Codex harness is actually open source. So you can go on and learn how the harness has been set up in Codex. It's a fantastic model. It's a fantastic app. You can go on and learn about it. But these are like early signs of how harness is going to go. And I expect that there are going to be a lot more problem and domain specific harness engineering that's going to take the model and then going to embed it within a very particular kind of decision-making process. Which takes me to the most exciting part of today's conversation, fleet of agents, right? The claws, right?
Yeah.
OpenClaw really took us all by storm, but now there's an entire stream of claw clones which are coming up. In what way do they act, and can you throw some insight into it?
Yeah, it's a wonderful segue into what is, I think, the most exciting thing about agentic AI today, which is bringing agentic AI to the realm of personal assistants. But I might be doing it a disservice by calling it just a personal assistant, because that term personal assistant is thrown around a lot. When you look at OpenClaw and a tool like OpenClaw, there are many clones of OpenClaw. I've come across a Pico Claw, I've come across a Nano Claw, and these are the same claw-based approach that involves agents written in different languages and with different footprints. So let me get into what a claw is exactly. You can call it an orchestration layer that sits on top of one or more LLM-powered agents. Right? So there are multiple LLM-powered agents that you want to use to execute different kinds of tasks. You have different channels through which you communicate with this agent or these multiple agents. You have the ability to execute tools. You have the ability to provide system instructions or prompts that guide or shepherd the behavior of this agent or these agents. And the net capability that you have is that through common interfaces that we use as humans, such as WhatsApp or Telegram or Discord, through these kinds of interfaces, you can kick off different kinds of agentic workflows that can be used for multiple use cases. OpenClaw is not a fundamentally new thing. If you look at the history of OpenClaw, and yes, to the observant outsider, it might look like OpenClaw and the capabilities that are within OpenClaw have been around for a while. And that is true. As people who are practitioners in this space, we both know that it's not a completely new thing, right? It's not a new model like the DeepSeek dropped a couple of years ago. It's not a completely new model like, say, Opus 4.6, which seemed to show some very high level capabilities. But it is an engineered system, and that engineered system is meant to using different channels solve the user's problems. It is a way to produce executable code. It is a way to produce deterministic executable code based on some kind of imperative user instruction, right? And this seems to be the big differentiator between, say, OpenClaw and a number of other agentic tools or frameworks out there, because the frameworks in the past have given you the Lego blocks with which you can build your Lego castle or your Lego car, but they've not given you the recipe. With OpenClaw, you're getting the recipe for putting those blocks together. OpenClaw's initiation process is a simple command line activity, right? So you do an OpenClaw init kind of a command, and you end up connecting it to your Discord and your email and this and that and everything else that you want to. Yes, we have also heard the flip side of this, which is some of the security issues that people have experienced, and those are legitimate concerns. But when you look at this as a technology capability, this is the sort of capability that can take somebody with an idea and turn them into a solopreneur. This is the kind of capability that can give each employee the ability to 2x or 3x or 10x their capability, right? So I feel like there's going to be a future where what they represent is going to become baked into the very nature of generative AI. So those were a number of different topics that we covered today. We started from large language models. We started from some of the nuts and bolts of how they're built and trained. And fast forward to later on, we talked about agents and we talked about multi-agent systems. We've talked about harness engineering and then clause. That's a lot of stuff that we've covered today. What would you like to cover in the second part? And you know that there's going to be a second part to this. Listen.
Absolutely. See, some of these things are quite exciting. I think the one that I'm really very bullish about is that there'll be claws that are very, very domain specific. So I know you've been building something in the space. So we will do a deep dive into the architecture of it. So there are two components to it, right? Like, okay, we have the base LLMs, reasoning LLMs, and now we have all the other things that go along with it, right? Your memory, your tool calling, MCP, and all the other things. So then we start doing agents. So we'll start the next one where we talk about how do we build a framework, like what are the common frameworks, and then we'll pick a framework which you have built and then dig deeper into it to know how one can go build a framework and what kind of use cases does it enable. We'll talk building a workflow system. We'll talk about a fleet of agents, agentic AI. And then we'll go deeper into the Claw ecosystem. And next time we'll do like a hands-on session where we can see the code, see how things work.
Exciting stuff. The second session is something I'm looking forward to. Bhargava mentioned a framework that I've been building. This is the Praval framework, and there's an associated class-like system called Praval Claw that I'm building, and I'd love to go into it with all of you in the next episode. So subscribe to our channel. There are a number of short videos that we release as part of this Hyperplane podcast series. In addition to the previous 3 episodes, there are going to be many more episodes, just like this one, which will be not just broad-based and talking about various kinds of phenomena and paradigms that we see in the space, but also very specific actionable information that you can take away and use in your work, whether you're an AI engineer or whether you're a software developer or any other kind of technology professional. There's a lot that you can gain from this series. Bhargav, would you like to add something else for our listeners?
You're going to love the next episode. I can guarantee that.